Okay, we are into our final chapter of the semester, and that is a chapter all about probability. So if you've taken a statistics course, some of this stuff is going to be things that you've seen before. We are focusing primarily on classical probability. If you haven't taken statistics yet, or you didn't need to take statistics, and you don't know what the difference between classical probability and that there was another type, don't worry about it. If you have, know that we're focusing on that. So in 9.1, this is our introduction into probability. So we're looking at two things in this section. It's a short section because we're just going to be taking a look at some key definitions and notation. Definitions and notations. And then secondly, we're going to be talking about counting. So let's jump in here. The first definition we have is sample space. And this pen is dying. So the sample space for our definition is the set of all possible outcomes of a random process or experiment. So when we say experiment, we mean a random process. So a statistical experiment is a random procedure that has some number of outcomes. And all of those possible outcomes are sample space. An event is a subset of the sample space. So if you think about rolling a six-sided die, so your sample space of outcomes is you can get a 1, a 2, a 3, a 4, a 5, or 6. Now, an event could be something like you roll an even number, and then that would be satisfied if you hit 2, 4, or 6. And so that's your event. It's a subset of your total outcomes. Now, with sample spaces and events, our next definition is equally likely probabilities. Probability. So if S is a sample space, for which each outcome is equally likely, then the probability of an event E, which would be defined as the probability I can spell, of event E occurring is P of E. So in this chapter, when we see capital P of something, you're always going to read that as probability of. So in the probability chapter only, whenever you see the P of an argument, that's the probability of that thing happening. So the probability of event E occurring is defined as the number of outcomes in E divided by the total outcomes in S. Or you can think of it as the size of E divided by the size of S. in set notation. So if we go back to that rolling a six-sided die example and the even event, so the number of outcomes in you rolling an even, there's 3 possibilities out of 6. You have a 1 out of 2 chance. And we know that to be true. That's essentially what classical probability is all about, is looking at those things that we know very well. So let's look at a different example just to kind of nail this home. Nail this home? Hammer this home. Nail it down. Those are the expressions. So let's say we have a deck of cards. Standard 52 card deck. And we are drawing 1 card. And we want to know what's the probability of drawing a jack, and what's the probability of drawing a jack of diamonds. So we look at how many jacks are there in a standard deck. There's 4. So the probability of drawing a jack is 4 out of 52, or 1 in 13 chance. And the probability of drawing the jack of diamonds specifically, there's only 1 of those out of the 52. So you can see the more general we get, the more likely we are to do it. That's why if you think of something like roulette, which has you bet on numbers and colors, obviously there's more bets in roulette than just that, but just those basic examples. Betting on a color is 50-50, 1 in 2 chance, black or red. Betting on an even number, there's exactly the same number of even numbers as there are odd numbers in roulette. Again, a 1 in 2 chance. So this is the idea of our probabilities for events. So now what we're going to talk about right now is a fun little problem called the Monty Hall problem, named for Monty Hall, the old show host. Might be before some of your time, most of your time. So, the Monty Hall show, they were given 3 doors, the contestants, and one has a prize. And you get to pick 1 door. And if you've ever seen the show, oftentimes Monty Hall would ask, do you want to switch after you've decided? If you want to switch. After looking in your door. Now, he's looking in your door, you're not looking at it. Now, we're going to ignore the fact that a lot of times, he wouldn't ask this every time, we're going to pretend that he did. And a lot of times he would ask knowing that they had already gotten the prize. But we're going to pretend that that's not the case. Just assume he asks everyone, he takes a look, you pick a door, he looks at the door, inside the door, and then he closes it and he says, do you want to switch your door? So what we want to do is figure out what maximizes the probability of winning. So in essence, do you want to switch or do you not want to switch? Switch or not. So you should take a few minutes to think about this. It's a fun little problem that really hammers down the essence of how probabilities work. And I like this problem a lot because it really shows where the kind of cultural perception or the societal perception of probability isn't quite what you would think. So think about it, pause the video. Seriously, I encourage you to pause the video here and think about this. Should you switch or not? And try and figure out rigorously using mathematics, using probabilities, should you switch or not. So now that you have hopefully paused and thought about this, I'm going to go through. There are 3 cases to this problem. All right, so case 1, you've already picked door A, door B, and door C. So let's say you've picked A. This is the one that you've picked. And the first case is that B and C are empty. You've picked correctly. The second case, again, we have A, we have B, and we have C. You picked A. It doesn't matter which one you picked. You picked one of them, right? It's just like our without loss of generality. You just pick a door. And in case 2, the prize is in B, and C is empty. And then in case 3, you guessed it, A, B, C. Again, you picked A. B is empty, empty, and the prize is in C. So these are the 3 cases that could happen. So I guess we could write picked prize here. We've already won. So what we want to be thinking about for probabilities is, what is the likelihood that we have selected the right door? Well, we know we have a 1 in 3 chance of picking the prize. So now we don't know which case we're in. How many of these cases have we not picked the prize, though? That would be 2. So in 2 out of 3 cases, we should switch. That means to maximize our probability of winning, 66% of the time, 66.6 repeating, we should switch. To maximize our probability. Because if we don't switch, we're still sticking with our 1 out of 3 chance. But if we switch, 2 out of 3 of those times, we're going to switch, and we're going to have switched correctly because we already did not pick the prize. So it kind of goes counterintuitively to what a lot of people think. Once you pick, it does make more sense, probabilistically, to switch your door. Now again, we're ignoring the fact that in the actual show, Monty Hall a lot of times looked at your door and asked, do you want to switch if you had the right prize? And sometimes he would look at your door and say, he wouldn't say anything. He said, are you sure? So again, we're kind of changing the conditions of this problem here a little bit, but this is the kind of the thing that we need to be able to wrap our heads around, is probability is very logical and extremely rigid. So we're not saying that we're going to win if we switch, but we have a better probability of winning because in these 2 cases, 2 out of the 3 cases, we've already picked wrong, and then we have a 50-50 shot of picking the right one. Now, if you're here and you switch, obviously you'll be upset, but that's only going to happen 1/3 of the time, 33% of the time. So those are the things that we're going to be thinking about. So let's look at a little theorem now about integers and how to count integers. So if n and m are integers, and m is less than or equal to n, then there are n minus m plus 1 integers from m to n. So this gives us a really fast way to count integers. So let's look at a little example, maybe 2 examples. You should try these, as always. Try this out. You have the theorem. See if you can suss it out. So how many integers are there from 7 to 1,132? Well, we have our integers. 7 is certainly less than 1132. So that means we have 1132 minus 7 plus 1. So that's really just minus 6. So that's 1126 integers. This is the counting principle that says that from 1 to 100, there are 100 integers, right? It's 100 minus 1 plus 1, which is 100. But from 0 to 99, there's 99 minus 0 plus 1, still 100 integers. Right? That's kind of the classic example that people get confused by. From 0 to 99, you're actually looking at 100 things. But if you start at 1, then you have to go to 100 to hit the 100 thing. So I want to give you, this would have been a practice problem, so definitely try this out on your own. So I would like to know how many integers has an n, from 100 to 999 divisible is not a p, divisible, are divisible by 5. Now I'll give you a little hint. You want to be thinking about how many multiples of 5 are there. So you should pause the video here and try and work this out. It's a fun little problem to think about. It's not super difficult, but it does require you to use this theorem and then stretch it a little bit. So I'm going to go through this. Hopefully you've already come up with your answer. So the way that we want to be thinking about this is if we want to know how many multiples of 5 there are, 5 times 20 is 100. And we're going up to 5 times 200 equals 1,000. Now, we can't get to the 200th multiple because we stop at 999. So instead, we're going to go up to the 199th multiple, which is 995. So we really are counting how many integers there are from 20 to 199. Because 5 times 20 is 100, so 5 times 21, 105 is in that range. 110, 115, 120, 130, all of those numbers, until we get to 995. So we're really just counting from 20 to 199, which by our theorem then would be 199 minus 20 plus 1, or 180. So there's 180 integers from 100 to 999 that are divisible by 5. So a little extension of this, what is the probability that one of these is chosen at random. So connecting it back to our probabilities now. So again, pause the video, think about it. I'm going to go through it now. So if we have 180 integers, essentially what we're saying is, what is the probability that the event that a number that's divisible by 5 is selected from all the integers from 100 to 999? So we need to know, first, how many total integers? I said 199, 999. So we want 999 minus 100 plus 1, which is 900 integers. And remember, our probability of an event happening is the size of that event divided by the sample size. So that's going to be 180 divisible integers out of 900 possible. Or, I'm going to sneak it in at the bottom here, this is a 1 in 5 chance reducing 20%. So that's kind of what we want to be thinking about. In this section, in this homework, you're going to be doing a lot of counting integer problems where it's based off of this theorem. You're going to have to think cleverly about it, just like this divisible by 5. Figure out, okay, how can I turn this into just a strictly counting problem? And then you're going to be asked some classical probabilities of questions like this. Okay, once you've counted up this thing, what's the probability that you actually select one at random? But like I said, this is a short little section. That's the end of 9.1.